Galileo Galilei, 1564 to 1642. He had a hypothesis that objects would gain speed at a constant rate. What that means is they would increase velocity at a constant acceleration, which we know to be true, but he didn't. So in order to test that, he wanted to measure a free-falling object's speed over time. So the change in speed over time, which we know as acceleration.
However, there is many problems to that, such as the first one would be cannot measure time accurately. Another thing is they also cannot measure speed accurately. And the third one was he doesn't know what gravity is. So,
the solutions. Number 1, use a water clock. The way that works is while the ball is rolling down the inclined plane, we are going to release water into a beaker. We will then measure the weight of that water, subtract the weight of the beaker, and the second solution is to compare the time that it takes the ball to go a certain amount of distance to the actual distance that it goes. And then we take that and compare it to the time that we got in solution number 1, and he found that the distance is proportional to time squared. Finally, we solve for gravity. Unfortunately, there were a couple more problems here, but we know that an inclined plane can be related to gravity because it's just when theta is 90 degrees. So when we bring that down to 45 degrees, it's half the angle. So it would be easy to measure theta if he had the tools to measure theta. Unfortunately, he did not. So we resorted to trigonometry. Sine of theta equals opposite over hypotenuse, which in this case is height of the inclined plane versus length that the ball will travel. So acceleration equals height over length times gravity. But because our theta was 45 degrees, we had to divide by 2, which means that the distance is equal to height over 2 times the length times t squared times gravity. When we rearrange that, we get that gravity equals 2 times the distance traveled times the length of the inclined plane divided by the height times t squared.
So for our ramp, I basically had one full wood that was like 91 centimeters by 26 centimeters. I cut it in half, so basically these two halves. Then we have like the middle, where that's where the ball goes. And we had a bigger ball, so it's just on the rim because of friction, to have less friction. Then the whole backboard is 1.5 feet to have the full length that we needed. Then right here was the wood, it's like 2x4 that we needed to have for like the height. I basically just cut a portion of the wood off to have like the angle right for the 90 degree. Then the bottom part is where the ball hits once it finishes 1.5 feet long. Then it just finished it off. There you go.
I took a Starbucks ice water cup, proceeded to melt a hole in the middle, and then we put rubber in that hole so that it would be waterproof.
Here's the ball.
All right, 3, 2, 1, go. Okay. There's that. Yep.
Since it's hard, just gotta go here. Just a bit more.
A little less.
Less? Should I be more?
Oh yeah, more my bad.
Yeah, I was like, wait, what? Just like one more, maybe?
Yeah.
Yep.
About
So it's 366.7.
366.7.
This is our data. You can see we have it labeled by trials, full, 3/4, halfway, 1/4. Down here we have the mean, then the standard deviation for each of those, and some various information such as length, height, mass of the beaker. Now moving over here, you can see that we calculated the times given the length ratios, then we did square roots, the plane ratio, we squared them, and we did them cubed. And the graphs look like this, with the length ratios on the x-axis and the y-axis being our times. The most linear one was, of course, the squared, And the equation for that was y equals 0.9269x. And then when we come back over here, the uncertainty of our slope and the uncertainty of our times and lengths.
So although our project was nearly flawless, we found slight errors in our project. One of the errors being that our actual inclined plane was the bare minimum measurements, and since there's the bare minimum, we had like fractions of seconds to actually be able to time the water going into our beaker. Also, us measuring the beaker was with the weighted scale, and we're not exactly perfect at it, so that's not, so we would mess up the grams, of course. Also, this thing has friction, like lots of it. This isn't as smooth as what Galileo probably did. And also our ball was made out of wood, so that also added friction to it. Our water mechanism was a finger. We had to stop the water with our finger, so we stopped it with our finger, we'd let go, and then we put our finger back in. So there was, of course, again, more human error. Yeah, I think that's it.
We will divide the water weight that is released in 1 second, so that way
It's like 91 centimeters by like 26 centimeters, cut in half, so half that all. That's that. Then basically you have the middle where the ball would have went, but we had a bigger ball, so it's just on the rim, just going all the way down.
And why did we do that, Andrew?
Because of
I didn't
friction.
realize you were actually
Yes, we're
recording.
recording.
Yes, we are
So,
recording.
Yes, and this is gonna be in the video too.
Do we have a blooper reel?
No, boo!
I do not want that.
I don't know how to tell them I'm recording.
Well, as long as I didn't curse, I'm fine. Did I curse in it? Don't worry. So how's your calculations going?
Oh!
Just about. Almost got it. You want to talk about it?
No.
Okay.
Like now?
Yes, now.
Do I look like I've been crying?
The 90 degree, then it's like a 45. And yeah, so the ball just goes down, hits it, and boom, we're done.